I guess I have the honor of bookending the series of great talks we've had here yesterday, and don't want to come too much in the path of lunch that I see waiting. It's been really an exciting 2 days. I'm going to rush through this. It's a lightning talk, so I'm try and fit in a whole bunch of slides in the next 15 minutes or so. So my name is Vikram Joshi. I'm the founder of ComputeAI. And today I'd like to talk about how to build a never say die system, a system that does not fail with memory failures. And that's what we are calling safeguarding against kills while not sacrificing performance. So how do you build high performance, high efficiency systems? And that's what Compute.ai has done. Initially, I'm going to go ahead and introduce what we do. And then a good part of the talk is on how do we plan to integrate. We are working closely with the Velox team here. And how do we integrate with Velox and contribute to the Velox community? So firstly, what's ComputeAI's mission? Our goal is to make compute completely abundant. And I think we've heard different thoughts on compute here today. For example, talking to some of the Velox people here at Meta, they are able to utilize the CPU to the limits. And that's a good thing. Also, the kinds of workloads that they're running, including with high concurrency, they don't see some of the problems that I think I saw William from Voltron talking about. When you start to do shuffling of data, you're doing more joins, you're doing more group buys, you're using more distributed systems, or you have to deal with skewed data, then you're going to do a lot of IOs. And people have implemented different strategies out there, whether it's different kinds of network accelerators or pushing stuff into GPUs to do that. And we have an approach to work with the IO weights that are incurred either due to networking or due to memory hierarchy. So if you're not going distributed, you're dealing with vertical memory hierarchy and you start to do demand paging or spilling to disk. And as we know, usually when you start to spill to disk, things go south. You want to take a coffee break, and how do you amortize some of the cost of spilling to disk and making things efficient? So making compute abundant is really, when you start to, if you look at just the TPCH and TPCDS benchmarks, especially at SF 100,000 and 10,000, for Presto, Spark, Trino generally, the numbers for most of the queries that are running, like in 5 to 8 node clusters, you scale typically because you want more memory, and it's more expensive to scale vertically, just the way that memory chips and memory density is being built. The cost structure doesn't allow that as to go vertically too much. So when you start to scale horizontally, you start to see more sharding and more shuffling. And as a result, the CPU utilization is of the order of about 9% to 25% is what we're seeing. So if you want to maximize compute, then you have to do something else out there. We view memory and processor cores as two sides of the same coin. And I think we'll get an opportunity to explain, have some resources at the end where there are some articles that have been written exactly on this, and that's been the focus of Compute.ai. How do you maximize compute, and how do you overcome some of these issues? The whole goal here has been to go after TCO, so the total cost of ownership for massive clusters. ComputeAI's platform is a single node system, and we focus on running clusters of very large number of nodes, say hundreds of nodes, where you can literally run millions of SQL jobs. And these are not the typical SQL jobs that you see here commonly in people typing SQL ad hoc or batch. This is high concurrency workloads with complex SQL, and I have a picture that actually talks about the specific use cases that we are targeting here. So this is not your typical data warehousing style cases. We are more after the use cases where you have autonomous sources of SQL being generated, very complex compute which is coming out there, low code, no code, semantic layer generation where you need large amounts of compute out there, and you cannot deal with low utilization of the CPU. The technology is also applicable to GPUs, which we may not get a chance to get into very much today. So that's about today's focus is mainly on the CPUs, though we have some prototypes now which will apply some of the technology that I'm going to describe here to GPUs. You have the issue of kills on GPUs and low CPU utilization there too. So this is the high-level architecture. And if you see the green box there, which calls the ComputeAI microkernel, that's really the focus of what we are doing. And what that allows you to do is do these low-level optimization. There is some overlap with what we heard earlier today from Audie on the wave kind of the product. However, the focus is mainly going to be on kills right now. But if you look at the architecture, we support different dialects of SQL, and the most popular dialects of SQL out there, open dialects are Presto and Spark. So this is not a Presto system. It's not a Spark system. We use open source components out there. And all we need is a SQL client. So there's a lot of similarity between what vlogs does and what we expect, which is just feed us a plan and we'll go ahead and execute it. But our focus, again, is on memory tiering, memory hierarchy, and compute efficiency. And we work directly on data lakes in the Parquet and the Iceberg side of the world. So here's another picture that illustrates what we do. And our product was initially built for some Wall Street customers, some large banks. And they had workloads that were already running on Spark, Presto, and Trino. But the issue of kills was coming in the way of TCOs. So typically, they'd have to run the same job about 10 times. And they actually put in a completely different infrastructure. This is one of the top 3 investment banks on Wall Street with over 10 petabytes of workload. And because of these kills, they'd have to rerun the jobs, and they had dashboards and stats which would tell them which machine had how much memory to reschedule the job, and restarting the cluster took about 8 minutes or 10 minutes. And that's where we come in. So think of us as a little router which actually runs the SQL too and executes the SQL, but these are the kinds of workloads which would be high reliability, and you send the normal workloads to other compute engines, and we are just another compute engine which deals with ultra-high concurrency and very complex compute. So the kinds of compute that we typically handle would be far greater in complexity. We are talking about hundreds of joins and massive working set explosions, especially when you're not able to predict the dynamic compressions and rarefactions in the data. Doesn't necessarily have to be the input size of the data. It could be what happens when you execute the plan dynamically. So that was the focus of what compute did. So the problem statement of what we tackle is pretty large and not something that we can cover here. What I've highlighted in red is what we're going to be looking at today. Infrastructure provisioning. So one of the things that we see with a lot of the open source products is to prevent the kill, you go ahead and provision memory for the worst case, which ends up at least on the cloud side with a lot more infra. And that means most of the time you're not utilizing the infra. If you have, maybe at Meta, it's highly optimized is what I'm hearing. However, in most businesses out there, people are not able to utilize the infra, or they don't have secondary and tertiary mechanisms that allow you to super recruit that infra for other kinds of use cases. So you end up over provisioning and underutilizing. And the same thing happens with CPUs and GPUs too. We already talked about the low utilization, the root causes behind that. Some of them have to do with networking, and the others have to do with vertical memory, demand paging of memory. The other issue that we won't have a chance to talk about, but which we tackle with our microkernel, is the memory stalls. Typically, if you're running tensor-like cores, and I'm talking about CPU style work, there is certain kinds of throughput-based computing where you actually run out of memory bandwidth. However, in most analytical workloads that we have seen, the reason why we see CPU stalling, and CPU stalls look like busy CPU to you. So even the 9 to 25 or 30% of the CPU that you see busy, a good part of that is coming from CPU stalls. And that is really a function of the pipeline flushes. So synchronization across the cores and mutexes, the slow path going inside the kernel, test and set kind of synchronization primitives, all of these cause processor pipeline stalls. And this is one of the reasons why you're not able to reach memory. So it's not that the memory bandwidth is being saturated, at least in the kinds of the analytics workloads that we're seeing, and those are the workloads that we are targeting. Now, the solution that we are focusing on for the kills, it has just 3 different components. We have a custom microkernel. Again, won't have a chance to get into the architecture, there is a data hypervisor that that has been built that actually looks at different tiers of memory. So typically you find 4 tiers of memory: DRAM, storage class memories, and then there is local SSDs, then there are remote. Typically there's not much spinning media out there, but you can find remote SSDs too, or shared file systems. And when you want to move, and then there are other newer technologies which are coming in, such as Ultra Ethernet, and then there is a CXL. How do you work with data across the memory tiers and allow different levels of data in the memory hierarchy? Think of your working sets, and large amounts of compute is going on. There's many different competing sources of SQL and SQL plans that are running, and there are different operators that are running in parallel. And how do you make sure that you're feeding the data just in time for the plans as they execute? So a lot of that entire work that we've done, the runtime, the microkernel, the way the threads are written, the way the plans are interpreted, the way the CBO, the cost-based optimizers work, it's all driven by AI ML itself. So we don't use the traditional models for demand paging of the yesteryear that we've grown up with and gotten used to, and also gotten a bit bored with it. And what we have done is we've thrown patterns at it, and we have a little neural net. The whole team has a lot of experience doing that. And with that, we are able to solve certain kinds of problems a bit better than before. So there is no night and day difference, and I'm sorry to let you down. You're not going to learn anything about memory. Ori mentioned that we have some innovation around what we do, but nothing fundamental around CPU and memory. I mean, it's the same thing as we always use, except that the kinds of problems that we tackle, we believe we have a solution that actually works. So just in time spilling to disk based on the plans and making data available, what is the underlying architecture that you need? That's what we are after. You won't get a chance to get into a threading runtime, so the stuff which is not in red and black, which is the thread local storage-based context switching, which is ultra light. It's of the order of a few microseconds. And the underlying tensor core style parallel processing, which allows us to do throughput-based computing. So I'm going to take a quick example here of what we do with our implementation for databases and what we do for hash joins. And this is your classic picture. You have a left table and a right table, or you have the probe side and you have the build side. And what's different here is, and once again, there's trees, there's bitmap, there's hash tables, and clustering on both sides. What's different here, the little nuance that we bring to the table, is that on the build side, when we start to partition tables, understand what we are trying to do. We are working in very tight, confined amounts of memory. And a system like ours, you can do terabyte-sized workloads. At some point, I'm hoping to be able to demo to the Velox community. Many terabyte-sized tables on both sides, and you can run them on 8 gig machines. There's no ohm kills. And will it run fast? No. But if you gave it more memory, are you going to be able to see some kind of a decent curve, maybe not linear? As you give more memory, it should go faster. So working through that, that's where the AI/ML comes into the picture, and how we exactly manage that, and how do we feed different competing plans, including SLAs. We have the ability to divide a machine with SLAs and actually tie a plan with an SLA and say, let's run some mixed workloads. This is throughput-based stuff, and here's latency sensitive, and you can partition those workloads, and the models learn on the fly. They learn by the patterns of the data. And actually, we are able to do a lot of work on the CBO side using this. So all we have done here in the circle marked in red is, on the build side of the table, if you are able to partition that table arbitrarily. So let's give you an extreme example of how that works. So a join, in our case, we look at the minimum number of pages that you need. There's 2 tables which are being joined, and there is 1 output table. So we need a minimum of 3 pages, something else for the metadata, and you can run any size join with that. And why does it not work today in some of the other architectures? One is maybe there was no need to have to push memory to the limit so aggressively, so we didn't have to go beyond the current in-memory architectures. And when we did the spill to disk, we didn't really go across all the algorithms. We took the most important ones, say hash join or hash merge or certain kinds of group bys, But if you look at relational algebra in the set of the operators, 20 or 25 of those, the most fundamental ones that we use, and all the variations of windowing and group wise and joints that we do, partitioning each of those and making them spellable is a fair bit of work. And what we do here in the highlighted area marked in red is that you can partition those pages on any arbitrary boundaries. You don't have to go into a row group or a partition size or anything. You can go in the size on not even MMU pages. You can go in very arbitrary, very small chunks using just malloc memory. So that's sort of in concept what we do, and that allows you to work with the minimum amount of memory. And if you gave it more memory, then you get a decent kind of a speed up, which is some kind of a function of the memory that you give it. Going forward, the entire infrastructure is, again, it's been inspired by some of my past lives being an MMU designer and working in virtual memory subsystems. So you really have the equivalent of page tables which are pageable, and everything is managed just as memory. There's the equivalent of a reference and a modified bit. There's scanning algorithms that actually use AI/ML, and as a result of that, you're able to actually there are cursors that page. Cursors can steal from other plans. You can steal from your own plan. The policies of who you steal from, who needs how much data, all of that is just machine learned. We come in as the system comes up, it calibrates itself. It figures out all the different sources of I/O, network throughput latency for different tiers of memory, and it's learning from the plan, and it's learning from the SLAs, and it's trying to do a best effort to make these kinds of things work. So the whole idea of this picture is that it's basically an MMU style design, which instead of using fixed page sizes, it uses malloc page sizes, and it's able to page to disk using some sparse mappings. Again, a lot of detail out there, but the whole idea of this talk was to at least communicate what we are doing with the spell to disk algorithms. So I'm going to just rush through this because I think it's going to be more detailed than what this talk can handle in such a short time. But what we are working with is, for cursors and pages, how much memory is there, how many concurrent plans, what are the operators, and what are the different kinds of trade-offs. And none of it is algorithmic, like I mentioned. Most of this stuff is really done in a heuristic fashion and seems to be working out reasonably well. We talked about SLAs. SLAs go into even stuff such as, I just created a table. These fields of interest are of use to me maybe 2 more operators down in the plan. How much should I keep it in memory? How much should I page? And cursors themselves are fairly aggressive in relinquishing the pages and saying, I don't need this. And that allows you to go out and do the steals and relinquish and free up the memory. And we handle both clean and dirty pages and transactional workload. Again, a little more detail here on the Steve pages. We talked about that briefly, but a lot of this is done in some of it in a cooperative fashion, and the worst case is obviously thrashing. You may have to eat from your own plan or somebody else's plan to make things actually work in the most contentious memory situations. You're not planning on that. The whole goal is you're not using your worst case infrastructure all of the time. You can give it an optimal amount of memory in the cluster, and in the worst case, when you do have a rare faction, your working set actually goes ahead and explodes, you're not facing an OOM kill. So that's the whole goal behind this whole thing. Don't run with the highest amount of memory all of the time. Memory is dear, is the most important, is the most expensive part of compute infrastructure, and your CPUs are not getting used. So those maybe not of interest to maybe people who are building processors and selling cores. You do want to sell as many cores as possible. It's more about the TCO. How can I utilize the compute that I have and make the most of the memory? So some of the takeaways here, the entire OOM kill prevention mechanism that we built in here, aside from the impact that it has on the operators, you have to rewrite the operators to be spell-fill, and they have to be pageable. So aside from that work, the memory overhead of this is really tiny. It's like 0.1%. So it's almost like even less than the typical MMU style page tables. And with very little memory overhead, we believe that we can actually make VLOC completely OOM kill proof safe. So that's the plan here. The slow path being when, the fast path is when you're doing your shredding and you're doing your computing with the cursors. And the slow path is when you run out of memory, you run out of a resource. You don't want to suddenly kill, and you want to go through a very gradual decay and a degradation out there, and that's what we manage. The slow path does not come and interfere with the fast path. And in these systemic and pathological feedback loops are the ones which we are trying to prevent. Making the slow path faster is not a goal, but making the slow path, kind of a gentler fall, not fall off a cliff, is where some of these ML heuristic algorithms come and play a role. And the architecture that we have is fairly generic, should work for the arrow style formats or whatever Velox uses and any other data model. What we use in memory, we believe, is far more optimal than, because we had a need to work with both hybrid page row-wise as well as column-wise page formats. And that's based on the plant dependencies. For example, you do want to do joinery with, say, more row-oriented kinds of page formats and memory. And how we pasted this, we saw the talk earlier on file formats. And I think there are some very interesting ideas that we can leverage out from there. But we do store data either as row groups or as columns, depending on how we need them later. So there's a fair amount of flexibility in the system here. So again, now, how does this play into Velox? So if you look at a stack, it's not very different from what the Velox stack is. And this is where we wish to come in and play a role. We didn't need to write our operators ourselves, because we are a generic platform which deals with compute efficiency, trying to make things kill safe, and trying to go after memory tiering. How do you deal with different kinds of tiers of memory, whether it's HBM memory, whether it's other sources of memory out there, and dealing with all of the data paths and dealing with the working sets and making it efficient for compute, whether it's CUDA kernels or whether it's actually databases or relational workloads. The other thing I didn't mention at the very start was this company was created to play at the confluence of relational algebra and AI/ML workloads. So while we have different kinds of frameworks out there, one of the most popular ones, one being the Apache Flume kind of framework to go ahead and run CPU, GPU-style models, whether it's for modeling or training. One alternative approach that some have started to use is you're mainly doing aggregations, right? Whether you're doing model sharding or you're doing data sharding, partitioning. And SQL works pretty damn well for that. So you can actually recruit your UDFs for super recruiting your GPUs. And with that, you could actually run massive workloads and do joinery, group bys, or whatever you're doing. Now toss in relational databases, whether you're doing RAG or you're doing vector style work, you put in graph knowledge databases. So vector databases, relational databases, graph databases, you're going to start to pull in, you're going to start to pull in tuples of information. Either they're going to be ordered or unordered, and you're going to have to do CPU and GPU work. So designing a microkernel that works at the confluence, at the juncture of these different kinds of databases, as well as CPU and GPU workloads, when you're running out of memory, and when whether it's in databases or whether it's on the GPU side. Now, there are certain kinds of GPU problems which are very latency sensitive, which is not of interest to us. But if you're dealing with very large contexts, very large batches, imagine contexts which are your entire movie or your entire GitHub repo, and it's going to give you a different quality of results. So those are the problems of great interest to us. And how do you automatically do different kinds of paging between different tiers of GPU and across? So that's the kind of work that the company is currently doing here. So we had no reason to actually go ahead, and if we had known about Velox, we would have not actually written the operators row code for a database. Instead, we would have just plugged that in, which is exactly what we are planning to do right now. And while doing that, we also believe that we can go ahead and contribute to the Velox community and make it kill safe and provide unlimited levels of overcommitment of memory. So we can actually go to whatever. There's no theoretical limit to how much overcommitment that you do, which is a big difference from running something in memory. And we do have our own performance numbers out here. We just compared with AWS EMR Spark, which generally runs about 2 times faster than Apache Spark. And we are about 2 times faster than AWS EMR Spark for all the way from SF1 to SF10,000. And we are running, apples to apples comparisons out there. And And obviously, it does not get unkilled. And typically, it uses about 3 to 5x less infrastructure. Our containers are on GitHub, so please feel free to download them and kick the tires. They're free to play with. And we don't have the full clustered product. For that, you'd have to contact one of us, and we'd be happy to get you going there. And there are some resources I'd like to point out here at the end. That's the end of my talk. Yep.